You have an incredible idea. A game-changing invention, a perfect custom part, a piece of art that only exists in your mind. You've spent hours, maybe even weeks, designing it on your computer. It's perfect. Now you just need to make it real. You upload your file to an online 3D printing service here in the US. You see a drop-down menu with a dozen cryptic names: PLA, ABS, PETG, nylon, SLA resin, MJF, and your heart sinks. What's the difference? You pick one that sounds good, you pay your money, and you wait. A week later, a box arrives. You open it, and inside is a disappointment. It's brittle. It warps in the sun. Snaps the second you try to use it. Your brilliant idea is now a piece of junk plastic, and you're back to square one, out 50 or $100. That exact scenario is the reason I'm making this video. The single biggest mistake people make, from garage inventors to professional engineers, isn't in the design. It's in the material. Choosing the right material is the difference between a revolutionary prototype and a pile of trash. And for the next few minutes, I'm going to give you the ultimate cheat sheet for the most common materials offered by online 3D printing services, so you never waste another dollar on the wrong plastic again. We're going to demystify this entire process, turning that confusing drop-down menu into your personal superpower. By the end of this, you'll know exactly what to choose for your project, whether you're building a BattleBot in your garage in Texas, designing a product for your Etsy shop in Oregon, or prototyping a new medical device in a lab in Boston. Let's start with the absolute workhorses of the 3D printing world. These are the plastics you will see on every single service, from the budget-friendly options to the high-end industrial printers. Think of them as the foundation of everything. We're talking about the big three: PLA, ABS, and PETG. First up is PLA, or polylactic acid. If 3D printing materials were a high school, PLA would be the friendly, popular, overachieving student president. It's the default, the go-to, the one everyone starts with, and for good reason. It's derived from renewable resources like cornstarch or sugarcane, making it one of the more eco-friendly plastics on the menu. Its number one superpower is its incredible ease of use. It prints with beautiful, sharp details, making it the undisputed king of visual prototypes and detailed models. If you're printing something that needs to look amazing sitting on a desk, a Dungeons & Dragons miniature, an architectural model, a character bust, PLA is almost always your best bet. It comes in a massive rainbow of colors, including specialty versions that look like wood, glow in the dark, or have glitter embedded in them. But like every high school president, PLA has a secret weakness. It's a bit of a lightweight. Its kryptonite is heat. Leave a PLA print in a hot car in Arizona in July, and you'll come back to a sad, melted puddle. It has a low glass transition temperature, which is a fancy way of saying it gets soft at around 140 degrees Fahrenheit. This means it's a terrible choice for anything that will be used outdoors, near an engine, or even holding hot coffee. It's also quite brittle. It's hard and stiff, which is great for detail, but if you try to bend it, it won't flex, it'll just snap clean in two. So, for a visual prototype to show investors? Perfect. For a functional gear in a high-torque machine? Absolutely not. Think of PLA as the material for things you look at, not things you use under stress. Now let's talk about PLA's tougher, more industrial older brother, ABS. You already know ABS. You've been using it your whole life. It's the same plastic that Lego bricks are made from. That should tell you almost everything you need to know. ABS, or acrylonitrile butadiene styrene, is all about durability and toughness. Its superpower is its resilience. It can handle much higher temperatures than PLA, up to around 220 degrees Fahrenheit, making it a fantastic choice for parts that need to survive in the real world. You can drop it, hit it, and it's more likely to deform or bend slightly rather than shatter. This makes it ideal for functional parts: drone frames, custom car interior pieces like vent covers or clips, and enclosures for electronics projects that might get warm. Another cool trick up its sleeve is that it can be vapor smoothed. By exposing an ABS print to acetone vapor in a controlled environment, you can melt the outer layer lines, creating a perfectly smooth, glossy, injection molded look. This is a pro-level finishing technique that's just not possible with PLA. But, of course, ABS has its own kryptonite. It can be a real pain to print. It has a tendency to warp and peel off the print bed as it cools, which is why most online services use professional, heated chamber machines to handle it. It also releases some pretty smelly, and potentially nasty, fumes during printing, which is another reason to leave it to the pros. It's less about fine detail and more about brute strength. So if you need a part that can take a beating and withstand some heat, And you don't mind if it's not quite as razor-sharp as a PLA print, ABS is your champion. It's the plastic for things that do stuff. So you've got PLA, which is beautiful but brittle. And you've got ABS, which is tough but tricky. What if you need something in the middle? What if you need the Goldilocks of plastic? That's where PETG comes in. PETG, or polyethylene terephthalate glycol modified, is the rising star of the 3D printing world. You might recognize the first part of that name, PET, which is the same plastic used to make water bottles. The G on the end is a simple modification that makes it perfect for 3D printing. PETG is the ultimate problem solver. It's a fantastic compromise, taking some of the best qualities of both PLA and ABS. Its superpower is being the best of both worlds. It's significantly stronger and more durable than PLA, with much better heat resistance. It's also more flexible, meaning it can take an impact without snapping. At the same time, it's far easier and more reliable to print than ABS, with less warping and no nasty fumes. It's also known for being food safe in its raw, unmodified form, which is why you'll see it used for things like custom cookie cutters or kitchen gadgets. Though always check with the specific service provider about their material's food safe certification. The layers of a PETG print also bond together incredibly well, creating parts that are very strong and often watertight. But it's not perfect. The kryptonite of PETG is that it can be a bit stringy. It has a tendency to leave little whisker-like strands of plastic on the finished print, which may require a bit more cleanup. It's also not quite as stiff as PLA or ABS, so for applications needing extreme rigidity, it might not be the top choice. And its surface is more prone to scratching than ABS. So, where do you use PETG? It's the ultimate material for functional prints that need to be tough, but don't require the extreme heat resistance of ABS. Think mechanical parts, protective phone cases, brackets, snap-fit enclosures, or even a custom watering can for your garden. It's the reliable, durable, do-it-all plastic that's quickly becoming the new default for engineers and makers across the country. So let's quickly recap. We have our 3 foundational plastics. PLA, the beautiful, easy-to-print material for visual models and prototypes that won't see heat or stress. ABS, the tough, heat-resistant Lego plastic for functional parts that need to survive in the real world. And PETG, the strong, durable, and easy-to-use middle ground, a perfect jack-of-all-trades for functional projects. Just by understanding the difference between these 3, you are already ahead of 90% of people using these online services. You can now make an informed choice that will save you time and money. But this is just the beginning. This is the ground floor. What about parts that need to be flexible like rubber? Or parts that need to be as strong and light as carbon fiber? Or materials that can withstand extreme chemicals and temperatures? That's where we're going next. We're about to leave the world of standard plastics and step into the high-performance engineering materials that are changing industries. So, what's the first step up from the everyday plastics like PLA or ABS? You've probably heard of nylon. But the nylon used in industrial 3D printing, typically called PA12, is a different beast altogether. Think about a high-quality zip tie. You can bend it back and forth, you can pull on it, and it refuses to snap. That incredible durability and flexibility is the core of what makes nylon so special. Unlike the rigid plastics we talked about before, nylon parts have a certain give to them. This makes them perfect for things like living hinges, snap-fit enclosures, or any part that needs to survive repeated stress and vibration without cracking. Most online services print nylon using a process called selective laser sintering, or SLS. Instead of melting a filament, a laser fuses together microscopic particles of nylon powder, layer by layer. The result is a part with a distinct, slightly grainy matte finish that looks and feels incredibly professional. And because the part is supported by all the unfused powder around it, you can create breathtakingly complex geometries without worrying about support structures. This process also gives the parts fantastic chemical resistance. They're largely unaffected by oils, greases, and many common solvents, which is why you see them used for durable prototypes and functional end-use parts in automotive and industrial settings. But what if you need nylon's toughness but with more rigidity? This is where composites come in. Services will offer versions of nylon that are filled with tiny chopped particles of other materials, like glass beads or carbon fiber. Glass-filled nylon, for example, is much stiffer and more resistant to wear and heat. It's a workhorse material for functional components like machine gears or durable housings that need to hold their shape under load. Carbon fiber-filled nylon takes it a step further, creating parts that are exceptionally stiff and strong while remaining very lightweight. This is a go-to for high-performance applications like drone frames, robotics components, and custom jigs and fixtures in manufacturing where every gram counts. Now, let's talk about brute force impact resistance. If you need a part that can take a serious hit and not shatter, you need to look at polycarbonate or PC. This is the same family of material used to make bullet-resistant glass and riot shields. It is, hands down, one of the toughest and most impact-resistant thermoplastics you can 3D print. If you were to print the same part in ABS and polycarbonate and hit them both with a hammer, the ABS part would likely crack or shatter. The polycarbonate part would just deform and absorb the impact. It's also optically interesting. While it's not perfectly transparent like a sheet of acrylic right off the printer, it can be post-processed to be nearly crystal clear. This combination of strength and potential clarity makes it ideal for things like protective guards on machinery, clear housings for electronics, or functional prototypes for products that will eventually be injection molded from the same material. Polycarbonate also has a much higher temperature resistance than ABS, so it can operate in hotter environments without warping or softening. The trade-off is that it's a notoriously difficult material to print with. It requires very high temperatures and is extremely prone to warping. This is one of those materials where using a professional service is a massive advantage. They have industrial-grade machines with heated chambers and precise temperature controls that are specifically designed to tame materials like PC and produce flawless, dimensionally accurate parts that would be nearly impossible to achieve on a desktop printer. So we have tough and flexible nylon, and we have impact-resistant polycarbonate. But what if you need something that rivals the properties of metal? What if you need something with an insane stiffness-to-weight ratio? That's when you enter the world of true high-performance composites, specifically continuous carbon fiber. Now, it's important to understand the distinction here. The carbon fiber-filled nylon we mentioned earlier has chopped fibers mixed in, like adding gravel to concrete. It makes the whole thing stronger. Continuous carbon fiber, offered by some specialized services, is more like laying down strands of rebar inside the concrete. The printer lays down a base plastic, like nylon, and then inlays a continuous strand of carbon fiber, or even fiberglass or Kevlar, inside the part at critical stress points. The result is revolutionary. You get a plastic part that has the strength and stiffness of aluminum, but at a fraction of the weight. This is a game changer for industries where weight is the ultimate enemy. Think custom robotics end effectors that need to be light and rigid to move faster. Think mounting brackets for performance vehicles, or lightweight fixtures for manufacturing assembly lines that reduce worker fatigue. We're talking about creating custom tools and parts that are strong enough to replace machined aluminum, but can be produced in a matter of hours instead of weeks, and at a much lower cost. This isn't just for prototyping. These are end-use, high-stress, performance-critical components. Okay, so we've gone from tough to strong to metal strength. But what lies beyond that? What material do you use when you're dealing with the most extreme environments imaginable? This is where we meet the undisputed kings of the polymer world. PEEK and PKK. PEEK, which stands for polyether ether ketone, is what's known as a high-performance polymer. And when we say high performance, we mean it. This material is in a class of its own. It has an incredible combination of mechanical strength, thermal stability, and chemical resistance. A part made from PEEK can operate continuously at temperatures over 480 degrees Fahrenheit, or 250 Celsius, a temperature that would turn most other plastics into a molten puddle. It is so chemically inert that it's resistant to almost everything except for some concentrated acids. It has outstanding wear and abrasion resistance, and it's even resistant to high levels of gamma radiation. Because of this, you find PEEK in the most demanding applications on and off the planet. It's used in aerospace for components that are exposed to extreme temperatures and jet fuel. In the medical field, its biocompatibility and ability to be sterilized repeatedly makes it a prime candidate for custom surgical instruments and even long-term medical implants. In the oil and gas industry, it's used for seals and sensor components that have to survive the crushing pressures and corrosive chemicals found deep underground. PKK is a close relative in the same family, offering similar properties but with a few of its own unique advantages, sometimes offering even better performance in specific areas. Printing these materials is exceptionally difficult, requiring printer extruders that can reach over 400 degrees Celsius and a meticulously controlled heated environment. This is the absolute cutting edge of polymer 3D printing, and the cost reflects that. A spool of PEEK filament can cost thousands of dollars. But for those applications where no other material can survive, where failure is not an option, the ability to 3D print a custom part out of PEEK or PKK is nothing short of revolutionary. We've pushed plastics to their absolute limit, from the flexible durability of nylon, through the impact-absorbing power of polycarbonate, to the aluminum-like strength of continuous carbon fiber, and finally to the extreme environment-proof performance of PEEK. We've created parts that can rival metal in certain applications. But what happens when you need the real thing? When you need the conductivity, the wear resistance, the unmistakable properties of pure steel, aluminum, or even titanium printed layer by layer. That's where the game changes entirely. Welcome to the world of metal 3D printing, a realm where the rules of manufacturing are not just bent, they're vaporized by lasers and rebuilt atom by atom. This isn't about melting plastic in a box on your desk. This is metallurgy meeting digital fabrication. It's the difference between a hot glue gun and a blacksmith's forge, scaled down to the microscopic level. The core challenge is immense. You have to melt and fuse particles of metal, which have melting points in the thousands of degrees, without the whole thing turning into a useless, warped blob. The two dominant technologies you'll find at major US-based online services to solve this problem are direct metal laser sintering, or DMLS, and binder jetting. And they could not be more different. Let's start with the undisputed king of complexity and performance, DMLS. You'll also see it called selective laser melting, or SLM. The names are slightly different, but the concept is breathtaking. Imagine you're an engineer designing a custom surgical implant, say a section of a jawbone. It needs to be incredibly strong, lightweight, perfectly matched to the patient's anatomy. And this is the magic part: it needs a complex, porous internal lattice structure so the patient's own bone can grow right into it, making it part of their body. You can't machine that. You can't cast it. It's what we call an impossible geometry. But with DMLS, it's just another Tuesday. Here's how it works. Inside a sealed chamber filled with an inert gas like argon to prevent the metal from oxidizing, a super thin layer of metal powder, finer than sand, is spread across a build plate. We're talking layers as thin as 20 microns. That's less than half the width of a human hair. Then a high-powered fiber laser, guided by your 3D model, zaps the powder. It doesn't just heat it up, it melts it completely, fusing the particles together into a solid cross-section of your part. The build plate then lowers by one layer's thickness. A new layer of powder is spread over the top, and the laser goes to work again, fusing the new layer to the one below it. This repeats thousands upon thousands of times, for hours or even days, until your solid metal jawbone implant, complete with its intricate internal lattice work, emerges from the powder bed. The result is a part that is nearly 100% dense. It's not a collection of sintered particles. It's a fully welded, homogeneous metal object with mechanical properties that can meet or even exceed those of a traditionally forged part. This is why DMLS is the go-to for the most demanding applications in the world. The material palette is a metallurgist's dream. You have titanium, specifically T64, which is the star of our medical implant story. It's incredibly strong, lightweight, and biocompatible, meaning the human body doesn't reject it. You have aerospace-grade aluminum like LC10Mg, perfect for creating lightweight, strong components for drones and satellites that would be impossible to machine. Then there's stainless steel 316L, a workhorse material you see in everything from marine applications to food processing equipment, due to its fantastic corrosion resistance. And for the really extreme environments, there's Inconel 718, a nickel superalloy that maintains its strength at scorching temperatures inside jet engines and rocket turbopumps. But this level of performance comes with a hefty price tag. The machines themselves cost upwards of $500,000. The process is slow, the specialized metal powders are expensive, and it requires significant post-processing. Because you're melting and cooling metal so rapidly, immense internal stresses build up in the part. To relieve these, the entire part, still attached to its build plate, has to be heat-treated in a furnace. And since each layer is built on the one below it, any overhanging features need to be supported by intricate metal scaffolding, also printed from the same material. These supports have to be painstakingly cut away by hand or with CNC machining, adding time and labor costs. So, for a one-off, mission-critical, unbelievably complex part, DMLS is unbeatable. But what if you need 50 parts? Or 500? The cost would be astronomical. This is where our second major technology, binder jetting, enters the scene. Imagine a different scenario. You're restoring a classic car, and you need a batch of 50 complex transmission gears that are no longer in production. The geometry is too tricky for easy machining, and casting would require expensive tooling for such a small run. DMLS is too expensive. You need a bridge between prototyping and mass production. That bridge is binder jetting. The process starts similarly with a bed of metal powder. But instead of a powerful laser, binder jetting uses a printhead that looks a lot like the one in your office inkjet printer. This printhead glides over the powder, selectively depositing droplets of a polymer binding agent, essentially gluing the metal particles together, one cross-section at a time. The build plate lowers, a new layer of powder is spread, and the process repeats. It's incredibly fast because you're not melting anything. You're just sticking powder together. A huge advantage here is that the surrounding unbound powder acts as a natural support. So you can nest dozens or even hundreds of parts within the build volume, stacked on top of each other, with no need for printed supports. When the printing is done, you have what's called a green part. It's fragile. It has the consistency of a sandcastle held together with a bit of glue. You can literally break it with your bare hands. The real magic happens in the next step: sintering. The green parts are carefully excavated from the powder bed and placed into a high-temperature furnace. The furnace first burns away the polymer binder. Then, it ramps up the temperature to just below the metal's melting point. At this extreme heat, the metal particles fuse together through a process called solid-state diffusion, shrinking and densifying into a solid metal object. The result is a metal part with good mechanical properties, typically around 97% dense. While not as strong as a fully welded DMLS part, it's more than strong enough for a huge range of applications, including our classic car gears. The key benefits are speed and scalability. Because the printing stage is so fast and you can pack the build volume with parts, the cost per part plummets as you increase the quantity. The materials most commonly used are stainless steels like 17-4PH and 316L, which are known to sinter very well. You'll see some tool steels and other alloys, but the selection is generally more limited than DMLS. The main trade-off is precision. The sintering process involves significant, uniform shrinkage. The part can shrink by about 20%. The software and service providers are experts at scaling the model up to compensate for this, but it introduces a level of dimensional variability that might not be acceptable for the tightest tolerance applications. So you have two incredible, yet fundamentally different paths to a printed metal part. DMLS is the laser-powered sculptor, meticulously crafting a single flawless masterpiece. Binder jetting is the efficient assembly line, producing batches of complex parts at a fraction of the cost. And just to add another fascinating option to the mix, some services are now offering a third way, often called bound metal deposition or something similar. Think of it as FDM printing, the kind you see with plastic filament but for metal. The filament isn't pure metal wire. It's a composite of metal powder held together by a wax and polymer binder. A desktop-sized machine extrudes this filament, layer by layer, to build your green part. Then, just like with binder jetting, that part goes through a multi-stage process. First, a chemical wash to dissolve most of the binder, and then a trip to the sintering furnace to fuse the metal particles. It's an even more accessible and often lower-cost entry point into metal printing, perfect for functional prototypes and fixtures. So when you upload your file to an online service and select titanium, you're likely getting a DMLS part. If you select stainless steel and order 100 units, you might be getting a binder jetted part. The choice of technology is driven by your material, your quantity, and the complexity of your design. We've gone from plastics that mimic properties to metals that are the real deal, forged in fire and lasers. But there's a whole category of materials we haven't touched yet. Materials that are rewriting the rulebook on strength-to-weight ratios. What if you could print a part as strong as aluminum, but at a fraction of the weight, using what is essentially a superpowered version of a desktop plastic printer? That's the world of fiber-reinforced composites, and it's where we're headed next. This isn't just about mixing some chopped-up fibers into a plastic soup and hoping for the best. That's been done for decades in injection molding. No, this is different. This is about laying down a continuous, unbroken strand of a supermaterial, like carbon fiber, fiberglass, or even Kevlar, directly inside a 3D printed part as it's being built, layer by layer. Think of it like this: a plain plastic part is like a block of concrete, strong under compression, but if you try to bend it, it snaps. Now, think about reinforced concrete. We embed steel rebar inside it. That rebar takes on all the tension and bending forces, making the entire structure exponentially stronger. In this world of 3D printing, the base plastic, usually a tough engineering-grade nylon, is the concrete, and the continuous fiber is the rebar. You are literally weaving a high-strength skeleton inside your part, precisely where it needs it most. The result is a material with a strength-to-weight ratio that is absolutely off the charts. We're talking parts that can match the strength of 6061T6 aluminum, the workhorse of the aerospace and machining industries, but at half the weight or less. This is why companies building high-performance drones, competitive race cars, and advanced robotics are so obsessed with this technology. Suddenly, you can create a custom robotic gripper that's strong enough to lift a heavy component, but light enough that the robot arm can move faster and more efficiently. You can design a structural bracket for an experimental aircraft that weighs almost nothing, but can withstand incredible forces. This isn't just an incremental improvement. It's a fundamental shift in what's possible. So how does it work? Imagine a standard FDM 3D printer, the kind that melts a spool of plastic filament. Now give it a second highly specialized print head. The first print head goes about its business, laying down the outer walls and internal fill of the part using a base plastic, often something like onyx, which is itself a nylon infused with microcarbon fibers for extra stiffness and a beautiful matte black finish. But then the second nozzle kicks in. It's not extruding melted plastic. Instead, it's meticulously inlaying a single continuous strand of fiber. It follows a precise path calculated by the software, ironing this fiber down into the still warm layer of plastic below it, effectively welding it into place. Layer by layer, the printer builds the plastic matrix and weaves this internal, high-strength fiber skeleton. The choice of fiber is where you really start to tailor the part to its job. The undisputed champion is carbon fiber. It has the highest strength-to-weight ratio of them all. It's incredibly stiff and strong, making it perfect for parts that need to resist bending and flexing under load. Think of it as the ultimate reinforcement for components that demand maximum rigidity. Things like support arms, mounting brackets, or inspection fixtures that cannot be allowed to deform even a little bit. But sometimes you don't want ultimate stiffness. Sometimes you need a bit of give, a bit of toughness. That's where fiberglass comes in. It's the rugged, all-around performer. It's still incredibly strong, about 2.5 times stronger than the base onyx material alone, but it's more flexible and impact-resistant than carbon fiber. Can take a hit. This makes it ideal for parts that might see some abuse. Plus, it's more affordable, and it has a unique superpower. It's electrically insulating and transparent to radio frequencies. So if you're building a housing for sensitive electronics or an antenna mount, fiberglass is your go-to. It provides the strength without interfering with the signals. Then there's the specialist, the bodyguard of the group, Kevlar. The same material used in bulletproof vests. Kevlar's claim to fame isn't stiffness. It's unparalleled toughness and impact resistance. It's designed for parts that will be repeatedly slammed, scraped, or subjected to sudden violent loads. Imagine soft jaws for a vise that need to grip parts without marring them, or a bumper on a robot that's going to be bumping into things all day long. Kevlar absorbs the energy and asks for more. It's exceptionally durable and resistant to abrasion. And for those extreme environments, there's even HSHT fiberglass, high strength, high temperature. It delivers similar strength to standard fiberglass but can survive in environments up to 150 degrees Celsius, or 300 degrees Fahrenheit. This opens the door to creating custom tools and fixtures for things like autoclaves, molds, or components that need to be mounted near hot engines. Now, here is the most critical piece of information, the part that separates the amateurs from the pros when designing for these materials. The strength is completely directional. A strand of carbon fiber is unbelievably strong along its length, but it offers no reinforcement perpendicular to it. It's just like a piece of wood. You can try with all your might to pull a 2x4 apart by its ends, and you'll fail. But take an axe to it, and you can split it right down the grain with a single swing. This means you can't just click a button that says "Add carbon fiber" and expect a super part to pop out. You have to think like a structural engineer. You have to analyze where the forces will be acting on your part. Where is it going to bend? Where is the tension? Where is the compression? Then you use the software to strategically route the continuous fiber along those load paths. You might lay down concentric rings of fiber around a bolt hole to prevent it from tearing out. You might run fibers along the top and bottom surfaces of a beam to resist bending, just like the flanges of a steel I-beam. The software that drives these machines is incredibly powerful. It lets you go in, layer by layer, and paint the areas where you want to add reinforcement. You can choose to fill an entire layer with fiber, or just trace the outer contours, or run it back and forth along a single axis. This level of control is staggering. It allows you to create parts that are perfectly optimized, placing strength only where it's needed, saving weight and material cost everywhere else. You're no longer stuck with isotropic materials, materials that have the same properties in all directions like a block of aluminum. You're creating an anisotropic composite, a strategically engineered structure where every single fiber has a purpose. Let me tell you about a real-world case. A company that automates manufacturing lines was using a robotic arm to pick up and move heavy metal castings. The gripper, or end effector, on this robot was machined from a solid block of aluminum. It was strong, but it was heavy. And because it was heavy, the robot had to move slower to manage the inertia, limiting the factory's overall production speed. On top of that, every time they had a new part to handle, it would take their in-house machine shop 2 to 3 weeks to fabricate a new aluminum gripper. They decided to try printing one with continuous carbon fiber. They redesigned the gripper, optimizing its geometry for 3D printing and identifying the key stress points. They ran long strands of carbon fiber along the gripper's fingers and reinforced the mounting points. They printed it overnight. The result? The new composite gripper was 75% lighter than the aluminum one. It was just as strong for the specific loads it experienced. Because it was so much lighter, they could crank up the speed of the robot arm, increasing their production throughput by over 20%. And now, when they need a new custom gripper, they don't wait 3 weeks. They design it in a day and print it overnight. The cost savings and efficiency gains were enormous. Of course, these materials aren't the answer for everything. Their strength is primarily in the XY plane, along the printed layers. The strength between layers in the Z-axis is still dependent on the layer-to-layer adhesion of the base plastic, which is a potential weak point. And while high-temperature versions exist, they still can't compete with the thermal resistance of steel or titanium for very high heat applications. This is a specific tool for a specific job. But for that job, creating lightweight, incredibly strong, complex parts for tooling, fixtures, and functional prototypes, it is revolutionary. It bridges the gap between the familiar world of desktop plastics and the high-performance world of machined metals. But it's still not metal. It's a simulation of metal's properties. What if you need the real thing? What if you need a part with the thermal conductivity, the surface hardness, the isotropic strength, and the raw, unapologetic performance of solid steel, or titanium, or Inconel? This raises a mind-bending question. How do you 3D print with something that melts at over 2,500 degrees Fahrenheit? It involves high-powered lasers, fine metal dust, and a process that looks like it's straight out of science fiction. And that's exactly where we're going next. Into the fiery heart of metal 3D printing. Imagine a dark, sealed chamber. Inside, a perfectly flat bed of metallic powder, as fine as dust, is spread in a layer thinner than a human hair. Now picture a high-powered laser, a beam of pure energy flashing across this surface. It moves with impossible speed and precision, tracing a complex two-dimensional shape. Everywhere the laser touches, the metal powder instantly melts and fuses to the layer below. The temperature at that tiny point spikes to thousands of degrees, a microscopic star igniting and extinguishing in a fraction of a second. Then a blade sweeps across, laying down a new dusting of powder, and the laser dances again, building the next layer. This process, repeated thousands upon thousands of times, is direct metal laser sintering, or DMLS. It's not just printing. It's microforging an object into existence, atom by atom, from a cloud of metal dust. This is where 3D printing sheds its hobbyist skin and becomes a revolutionary industrial force. Let's start with the undisputed workhorse of the metal printing world. Stainless steel, specifically 316L. You know this material. It's in your kitchen sink, your watch, and the surgical tools in a hospital. It's trusted because it's strong, incredibly resistant to corrosion, and can be polished to a brilliant shine. But when you take this familiar, reliable metal and put it into a DMLS machine, the ordinary becomes extraordinary. Because now you can create stainless steel parts with geometries that are flat out impossible to make any other way. Think about a company that designs custom brewing equipment. They need a specialized nozzle that can mix fluids in a very specific, turbulent way to optimize flavor. Using traditional machining, they'd have to create multiple pieces, drill channels, and then weld them all together. The result would be a clunky assembly with weak points at every seam. With 3D printing, they can design the nozzle as a single monolithic part, with smooth, organically curved internal channels that swirl and mix liquids with perfect efficiency. There are no welds to fail, no seams to trap bacteria. It's a stronger, more efficient, and more hygienic part, printed in a material that's already certified as food safe. That's the power of metal 3D printing. Taking a material we already trust and unlocking a level of design freedom that was previously pure science fiction. It's the go-to for durable prototypes, custom jigs and fixtures on an assembly line, or any part that needs to withstand a tough environment without breaking the bank, at least by metal printing standards. But what if your primary concern isn't just strength, but strength without the weight? What if every single gram is your enemy? Then you move from the workhorse to the racehorse. Aluminum. Specifically, an alloy like LC10Mg. This is the stuff of aerospace dreams and high-performance automotive ambitions. Pure aluminum is relatively soft, but this alloy is packed with silicon and magnesium, giving it a fantastic strength-to-weight ratio. It's light, strong, and great at conducting heat. When you pair these properties with 3D printing, you can create designs that look almost alien. Imagine a structural bracket for a racing drone. A traditionally machined block of aluminum is strong, but it's a solid chunk of metal. It's heavy. Using advanced software, an engineer can run a simulation to see exactly where the stress flows through that bracket during flight. The software then carves away every single bit of metal that isn't absolutely essential for carrying that load. The result is a skeletal web-like structure. It looks organic, almost like bone. It's incredibly lightweight but just as strong as the original solid block. You simply cannot make this part with a drill or a mill. You have to grow it layer by layer. This is called generative design, and it's aluminum 3D printing's killer app. It's why you see these parts on satellites, in Formula One cars, and on high-end bicycles. It's for when you need a strong metal part, but it feels almost impossibly light in your hand. So we have the tough-as-nails workhorse in stainless steel, and the lightweight champion in aluminum. But what if you need the absolute best of both worlds? What if you need a material that's stronger than steel, lighter than steel, and is so resistant to corrosion and heat that it laughs at environments that would turn other metals to dust? And what if it also needs to be so biocompatible that the human body literally accepts it as its own? For that, you need the superstar. You need titanium. The most common alloy, T6Al4V, is a legend in materials science. It has the highest strength-to-weight ratio of any commonly available metal. This is why it's the foundation of modern jet engines and the airframes of fighter jets. But its most profound application is inside the human body. Because titanium is biocompatible, our bone will literally grow onto and fuse with its surface in a process called osseointegration. This makes it the perfect material for medical implants. Now consider this. A patient has a section of their jaw removed due to cancer. In the past, surgeons would have to take bone from another part of the body like the hip or leg and try to shape it to fit. It's a brutal, inexact process with a long recovery time. With 3D printing, doctors can take a CT scan of the patient's skull, digitally model a perfectly fitting jaw implant, and print it from medical-grade titanium powder. The implant can be designed with a porous, lattice-like surface that encourages bone to grow right into it, making the implant a permanent, integrated part of the patient's own skeleton. This isn't a case study from the future. This is happening in hospitals right now. It is a life-changing application that is only possible because we can print with this incredible metal. Of course, with this level of performance comes a significant cost. Printing in titanium can be an order of magnitude more expensive than printing in aluminum, which is itself an order of magnitude more expensive than printing in nylon plastic. So why would anyone choose this path? It comes down to solving impossible problems. You choose metal 3D printing when the geometry is too complex to machine. Think of a fuel nozzle for a rocket engine, which has hundreds of tiny, intricate internal cooling channels that are essential for preventing the nozzle from melting. You can't drill those channels. You have to print them. You also choose it for part consolidation. A team of engineers at GE famously used 3D printing to combine over 20 individual pieces of a jet engine fuel injector into a single printed component. The new part was 25% lighter and 5 times more durable. That's a revolutionary improvement in an industry where a 1% gain is considered a massive victory. And finally, you choose it for bespoke, high-value parts like that custom titanium jaw. When the cost of failure is astronomical or when a part needs to be perfectly tailored to a specific purpose, the high price of metal printing suddenly looks very reasonable. But it's critical to understand that the price you see online is just the beginning. Metal parts don't just pop out of the printer ready to go. They're attached to a thick metal build plate by support structures, which have to be cut off with a wire EDM or a bandsaw. The part then needs to go into a furnace for heat treatment to relieve internal stresses built up during the rapid heating and cooling of the printing process. Without this step, the part could warp or even crack. And finally, critical surfaces often need to be CNC machined to achieve the tight tolerances and smooth finish required for the final application. All of this post-processing adds significant time and cost. We've journeyed into the fiery core of 3D printing, forging parts from steel, aluminum, and titanium dust. We've built the rigid, the strong, the unbendable. But the world isn't just made of hard things. What happens when you need a part that can stretch, compress, and snap back into shape? What if you need to print a seal, a gasket, a shoe sole, or a flexible grip? We've built with metal, but now we need to build with bounce. The next frontier isn't about ultimate strength, but ultimate flexibility. We're about to dive into the surprisingly soft, resilient, and rubbery world of elastomeric polymers, where 3D printing gets a whole lot more flexible. And flexible is an understatement. For everything we've discussed so far, the strength of polycarbonate, the toughness of nylon, the utility of PETG, they all share one fundamental trait. They are rigid. They are designed to hold a shape, to resist force, to be a solid object. But what if the entire point of your object is to not be solid? What if its function is to bend, to stretch, to compress, and to bounce right back thousands of times without breaking? This is where an entirely different class of materials takes the stage, and it's arguably one of the most exciting areas in 3D printing today. We're talking about thermoplastic elastomers, or TPEs, but the undisputed champion you'll find at nearly every online service is a specific type called TPU, thermoplastic polyurethane. Think of TPU as the ultimate hybrid. It has the processing ease of a plastic. It melts, flows, and solidifies just like the other filaments we've covered. But at room temperature, it behaves like a durable, resilient rubber. This single characteristic shatters the boundaries of what a 3D printed part can do. Suddenly, you're not just printing static brackets and enclosures. You're printing dynamic, interactive objects. You're printing gaskets that form a perfect seal, custom phone cases that absorb shock, shoe soles that provide cushion and spring, and soft robotic grippers that can handle a ripe tomato without turning it into juice. The key property we need to understand with TPU is its hardness, which is measured on a scale called the Shore Hardness Scale. This is crucial because flexible is a vague term. A car tire is flexible, but so is a rubber band. They are worlds apart in their properties. The Shore scale gives us a number to quantify that. Most TPU filaments offered by printing services fall on the Shore scale. For context, a gummy bear might be around 20A. A typical rubber band is about 25A. The sole of a running shoe is often between 50 and 70A. And the TPU you'll most commonly find for 3D printing is around 95A, which feels like the hard rubber on a skateboard wheel. It's firm, but you can definitely bend and squish it with your hands. Some services also offer softer variants, like 85A, which feels more like a durable shoe heel. This ability to choose a specific hardness level is a game changer for product designers. You can dial in the exact amount of flex your part needs. But flexibility is only half the story. The U in TPU polyurethane gives it a superpower: incredible abrasion and wear resistance. This stuff is tough, really tough. You can scrape it, drag it, and stretch it, and it just holds up. This is why it's used for things like industrial drive belts, caster wheels, and protective linings inside pipes carrying abrasive materials. When you 3D print with TPU, you're not making a flimsy novelty toy. You're making a functional engineering-grade flexible part that is built to last. It also has excellent resistance to oils, greases, and many chemicals, making it perfect for custom seals and gaskets in automotive or machine applications. A mechanic could design and print a custom, one-off gasket for a vintage car part that hasn't been manufactured in 50 years, and have it in his hands the next day. That's the power we're talking about. Furthermore, TPU has phenomenal layer adhesion. Because the material is so pliable when it's printed, the layers fuse together on a molecular level, creating an incredibly strong bond. With rigid plastics, you can sometimes find the grain of the print and snap it along the layer lines. With TPU, that's nearly impossible. The part behaves as a single solid piece of rubber. You can stretch it, twist it, and compress it, and the layers will not separate. This is critical for any part that will be repeatedly flexed during its life. So where are people actually using this? The applications are exploding. In prototyping, it's a miracle material. Imagine designing a new handheld electronic device with integrated soft touch buttons. In the past, you'd 3D print the hard plastic shell, but then you'd have to simulate the buttons or wait weeks for an expensive silicone mold to be made. Now, with dual extrusion printing, services can print the rigid ABS case and the soft, flexible TPU buttons all in one go, in one piece. You get a prototype that looks and feels almost exactly like the final product overnight. This drastically speeds up product development. In the world of custom solutions, TPU is king. We're seeing a revolution in ergonomics. Companies are creating custom-printed grips for power tools, bicycle handlebars, and video game controllers that are perfectly molded to the user's hand. Physical therapists are printing custom orthotic insoles and braces, tailored to a patient's specific anatomy. In robotics, engineers are printing soft, compliant grippers that can pick up anything from a delicate light bulb to a heavy, oddly shaped component without needing complex sensors. The gripper simply conforms to the object's shape. And then there's the consumer world. Custom phone cases with intricate designs and unbeatable shock absorption. Flexible watch bands printed in any color or style you can imagine. Vibration dampeners for drones, preventing the shaky jello effect in aerial footage. Even protective gear, like custom-fit gaskets for goggles or soft pads for sports equipment. The possibilities are truly as boundless as the designer's imagination. Now, how does TPU stack up against the other materials we've discussed? Well, against PLA, ABS, and PETG, it's no contest in terms of flexibility and durability. Those are rigid plastics. TPU is an elastomer. It's a different tool for a different job. The more interesting comparison is with nylon. We talked about how nylon is tough and has some flexibility, but it's more of a semi-rigid material. You can bend a thin piece of nylon, but it will snap back sharply. TPU has a deep, cushioned, rubbery flex. A good rule of thumb is, if you need a part to survive high impact and wear but remain mostly rigid, choose nylon. If you need the part to actively bend, stretch, or compress as its main function, you need TPU. You might also see the term TPE offered by some services. It's important to know that TPE is the broad family name for all thermoplastic elastomers, while TPU is a specific class of TPE. Think of it like this: sports car is the family, and Porsche is a specific type. Generally, TPU is the easiest of the flexible materials to print, offering a fantastic balance of flexibility, durability, and detail. Other TPEs can be even softer and stretchier, more like a rubber band, but they are notoriously difficult to print well, so you'll see them offered less frequently by mainstream services. However, this brings us to the challenge of printing with TPU. It's often described as trying to push a wet noodle through a small tube. Because the filament itself is so flexible, it can easily buckle, stretch, and jam in the mechanisms of a standard 3D printer. It requires a specialized type of extruder, called a direct drive extruder, which keeps the path from the drive gear to the hot nozzle extremely short and well constrained. It also demands very specific printing parameters, slower speeds, no retraction, and precise temperature control. This is one of the strongest arguments for using an online 3D printing service for flexible parts. They have fleets of professional machines perfectly calibrated for materials like TPU. They've already gone through the trial and error, the hundreds of hours of testing, to figure out how to print it perfectly every single time. You just upload your model, select TPU 95A, and you get a flawless, durable, flexible part delivered to your door, sidestepping all the frustration. In terms of cost, TPU is a premium material. You can expect it to be more expensive than standard plastics like PLA and PETG, often falling into a similar price bracket as engineering materials like nylon and polycarbonate. But for that price, you are unlocking a capability that simply wasn't accessible to the average person just a decade ago. The ability to create custom, durable, rubber-like parts on demand is a paradigm shift. It closes the gap between the hard, unyielding world of plastics and the soft, compliant world of rubbers. TPU has fundamentally changed the game, proving that 3D printing isn't just for making hard objects. It's for making functional, dynamic, and resilient systems. But what if your system needs to operate in environments that would destroy even the toughest TPU? What if you need a part that can survive not just impact, but extreme, unrelenting heat, caustic chemicals, and intense radiation? For that, we have to leave the world of conventional plastics behind and enter the realm of ultra-performance polymers. These are the materials that are replacing metal in the most demanding jobs on and off the planet. Let's start with the undisputed champion, the material that engineers mention in hushed, reverent tones, PEEK. That stands for polyether ether ketone, and it is, without a doubt, the gold standard of high-performance thermoplastics. If plastics had a royal family, PEEK would be sitting on the throne. Its combination of properties is so extreme, It almost sounds like science fiction. First, let's talk about heat. Most plastics, even tough ones like ABS or nylon, start to get soft and lose their strength well below the boiling point of water. PEEK, on the other hand, laughs at heat. It has a continuous service temperature of around 250 degrees Celsius, or 482 degrees Fahrenheit. To put that in perspective, that's hot enough to bake a pizza, and PEEK can just sit there day in and day out under mechanical load without breaking a sweat. Its melting point is even higher, a staggering 343 degrees Celsius. This isn't just a party trick. It means PEEK can be used for components inside jet engines, in high-temperature bearings, and as seals in downhole drilling equipment where temperatures and pressures are biblical. But its superpowers don't stop there. PEEK is almost chemically invincible. It exhibits extraordinary resistance to a massive range of organic and inorganic chemicals, aggressive acids, industrial solvents, jet fuel, hydraulic fluids. Most of the things that would dissolve lesser plastics barely even register to PEEK. This chemical inertness, combined with its ability to be sterilized repeatedly using steam, gamma radiation, or ethylene oxide, makes it a star in the medical field. And I don't just mean for surgical tools. I mean for things that go inside the human body. PEEK is biocompatible, meaning the body doesn't reject it. It's used to make spinal fusion cages, cranial implants, and bone screws. Its stiffness is even remarkably similar to human bone, which helps reduce stress shielding and promotes better healing. Think about that for a second. This is a 3D printable plastic that is strong enough to replace metal and safe enough to rebuild the human skeleton. Mechanically, it's a beast. It has a phenomenal strength-to-weight ratio, rivaling that of aluminum but at about half the density. It's tough, has excellent fatigue resistance, and a low coefficient of friction, making it ideal for high-wear applications like piston parts, pump gears, and valve seats. It's basically a material that lets you have the strength of metal without the weight or the risk of corrosion. So why isn't everything made of PEEK? Well, printing it is a monumental challenge. To properly process PEEK, you need an industrial-grade 3D printer that looks more like a furnace. The nozzle temperature has to be cranked up to around 400 degrees Celsius, the print bed needs to be heated to over 120 Celsius, and the entire build chamber has to be actively heated to well over 100 degrees Celsius to prevent the part from warping and cracking itself to pieces from internal stresses. This is not something you can do on a desktop machine in your garage. This is the domain of specialized online services with highly controlled industrial equipment, which is why PEEK parts command such a premium price. Now, right next to the king stands a very close relative, PKK, or polyether ketoneketone. At first glance, PEEK and PKK seem almost identical. They share that same family name, that same incredible resistance to heat and chemicals, and that same jaw-dropping mechanical strength. But there's a subtle, crucial difference in their molecular structure that gives PKK a unique advantage in the world of 3D printing. The secret is in its crystallization rate. PEEK has a very fast rate of crystallization. As it cools from a molten state, its polymer chains snap into a highly ordered, crystalline structure very quickly. This is great for final part properties, but it can be a nightmare during printing, as this rapid change causes significant shrinkage and stress. PKK, however, has a much slower, more controllable rate of crystallization. By precisely managing the cooling process during printing, engineers can essentially tune the molecular structure of the final part. They can choose to keep it more amorphous or disordered, which results in fantastic layer adhesion and toughness, making it perfect for printing parts with incredibly complex geometries that might otherwise delaminate. Or they can anneal the part after printing to achieve a higher level of crystallinity, maximizing its mechanical strength and chemical resistance to be more like PEEK. Think of it this way. PEEK is like a perfectly forged sword, incredibly strong but rigid in its properties. PKK is like having a material with a built-in dial. You can turn that dial towards amorphous, for better printability and z-axis strength, or turn it towards crystalline, for maximum thermal and chemical performance. This tunability makes PKK a favorite in the aerospace and satellite industries, where they need to print incredibly complex, one-off parts like brackets and housings that are both lightweight and can survive the vacuum and extreme temperature swings of space. It offers a level of processing freedom that even PEEK can't match. Rounding out our trio of ultra-performance polymers is a material you've probably flown with dozens of times without ever knowing it. Ultem. Ultem is the trade name for PEI, or polyetheramide. While it might not have the absolute peak temperature resistance of PEEK, it brings its own formidable set of skills to the table, particularly in the realm of safety and certification. Ultim is an absolute workhorse. It's incredibly strong, very stiff even at elevated temperatures, and dimensionally stable. But its killer feature, the one that makes it indispensable to the aerospace and transportation industries, is its FST rating. FST stands for flame, smoke, and toxicity. Ultim is inherently flame retardant without needing any additives. When you expose it to a flame, it resists ignition, and when it is finally forced to burn, it generates extremely low levels of smoke and toxic fumes. This isn't just a nice-to-have feature, it's a life-or-death requirement. The FAA and other global aviation authorities have incredibly strict regulations about the flammability of materials used inside an aircraft cabin. In the event of a fire, you need materials that won't contribute to the blaze or fill the cabin with blinding toxic smoke. Ultim passes these tests with flying colors. That's why it's used all over aircraft interiors for things like paneling, personal service units above your seat, electrical connector housings, and components for food and beverage systems. Beyond its FST rating, Ultim is also an exceptional electrical insulator with high dielectric strength, making it perfect for high-voltage applications. It's also resistant to a wide range of automotive fluids and chemicals, so you'll find it under the hood in sensors and throttle body components. Compared to PEEK, it's generally a more cost-effective option and is slightly easier to print, though it still requires a high-performance machine with a heated chamber. So you have this incredible trifecta of materials. PEEK, the uncompromising king of performance, used for medical implants and hostile industrial environments. PKK, the tunable specialist, offering unparalleled design freedom for complex aerospace parts. And Ultim, the certified FST-rated champion, keeping us safe at 30,000 feet. These polymers have fundamentally changed what is possible, creating plastic parts that don't just compete with metal, but in many cases, outperform it. They are lighter, more complex, and immune to corrosion. But what if even this isn't the final frontier? What happens when you take these already incredible superpolymers and decide to make them even stronger? What happens when you start infusing them, thread by thread, with materials like carbon fiber and glass to create the next level of 3D printed parts? Advanced composites. Think about reinforced concrete. On its own, concrete is incredibly strong when you try to crush it, but it's relatively weak if you try to bend or pull it apart. So what do? We embed steel bars, rebar, inside it. The steel provides the tensile strength, the ability to resist being pulled apart, and the concrete provides the compressive strength. Together, they create a material far superior to either one on its own. This is the fundamental principle behind composites. We're taking a great base material, a polymer matrix like nylon, and strategically introducing a reinforcing fiber to create a hybrid with superhuman properties. This reinforcement happens in two main ways in the world of 3D printing. The first and most common is using chopped fibers. Imagine taking tiny, microscopic strands of carbon fiber or glass, almost like a powder, and mixing them directly into the raw plastic filament. As the part is printed, these fibers are suspended randomly throughout the material. It's like adding sprinkles to ice cream, they're everywhere, and they make the whole thing a bit more rigid and strong in every direction. This is what you get with materials commonly listed as nylon CF or nylon GF. It's a fantastic way to boost the performance of a standard polymer, increasing its stiffness, strength, and thermal resistance significantly. It's a step up for sure. But the second method is where things get truly revolutionary. This is called continuous fiber reinforcement, or CFR. Instead of just mixing and chopped fibers, this process involves inlaying a continuous, unbroken strand of a reinforcing fiber, like carbon fiber, fiberglass, or even Kevlar, directly into the part as it's being printed. This isn't like sprinkles in ice cream. This is like laying down that steel rebar inside the concrete, precisely where the stress is going to be. The printer lays down a layer of the base plastic, usually a tough onyx or nylon, and then a second nozzle comes in and traces the path where strength is needed, embedding that continuous fiber. The result is a part with a thermoplastic exterior and a composite fiber skeleton. It allows for an unprecedented level of control, letting you design parts that have strength precisely where they need it, creating an internal architecture that can rival the strength of machined aluminum, but at a fraction of the weight. Let's start with the king of stiffness to weight, carbon fiber. When you see a part printed with carbon fiber reinforcement, whether chopped or continuous, you're looking at a material designed for high performance. Continuous carbon fiber, in particular, has a stiffness-to-weight ratio that is simply off the charts. It's stronger and stiffer than 6061 aluminum, but less than half the weight. This is why it's the material of choice in aerospace, Formula One racing, and high-end sporting goods. In 3D printing, it translates to creating incredibly rigid and stable parts. Think about robotic arms on an assembly line. The end-of-arm tooling needs to be extremely light so the robot can move quickly and efficiently, but also incredibly stiff so it doesn't flex or vibrate when positioning components with sub-millimeter accuracy. Printing a custom gripper out of continuous carbon fiber allows you to create a tool that's perfectly shaped for the task, weighs next to nothing, and is as rigid as a block of metal. We also see it in jigs and fixtures used in manufacturing, custom camera mounts for drones where vibration is the enemy, and even in high-performance automotive parts where every ounce of weight savings translates to faster lap times. The trade-off? Carbon fiber is one of the more expensive reinforcement options, and while it's incredibly stiff, it can be more brittle. It doesn't like to bend. It prefers to hold its shape or under extreme load break. Now, what if you need a boost in strength and stiffness, but the extreme performance and cost of carbon fiber is overkill? That's where glass fiber or fiberglass comes in. Fiberglass is the workhorse of the composite world. When used as a continuous fiber reinforcement, it can make a part about 2.5 times stronger and 7 times stiffer than just the base onyx or nylon material. While that's not quite at the level of carbon fiber, it's a massive leap in performance for a fraction of the cost. It's the smart economic choice for a huge range of applications. But fiberglass has another superpower that carbon fiber doesn't. It's an excellent electrical insulator. Carbon fiber is electrically conductive, which can be a deal breaker for electronic housings or fixtures that will be used near sensitive circuits. Fiberglass, on the other hand, is RF transparent and doesn't conduct electricity, making it perfect for those applications. You'll see it used in functional prototypes that need to withstand real-world testing, custom mounting brackets for industrial sensors, and durable consumer products that need to be rigid without breaking the bank. It offers a fantastic middle ground, providing metal-like strength where you need it, with the affordability and electrical properties of a polymer. But what if your primary concern isn't stiffness or cost, but pure unadulterated toughness? What if you need a part that can take a punch, absorb an impact, and survive a catastrophic event? For that, you turn to Kevlar. The same material used in bulletproof vests and puncture-resistant tires brings its legendary durability to 3D printing. As a continuous fiber reinforcement, Kevlar provides incredible impact resistance and energy absorption. It's not as stiff as carbon fiber or even fiberglass, but it has the highest abrasion resistance and is the most ductile of the three. This means it can bend and deform under load without failing. Think about soft jaws for a vise that need to clamp down on a delicate part without marring it, but also need to survive being used day in and day out. Or imagine landing gear for a high-end commercial drone. You want the frame to be stiff, so you might use carbon fiber there, but for the parts that actually touch the ground, especially during a rough landing, you want Kevlar. It can absorb the shock of impact that would shatter a more brittle material. It's for applications that require extreme durability and failure resistance, parts designed to be the last thing to break. So why are we so obsessed with these fiber-reinforced parts? Because they represent a fundamental shift in what's possible. We're no longer just making plastic parts. We are engineering materials on a microscopic level, layer by layer, to meet specific performance requirements. This is how you achieve true metal replacement. You can design a bracket for an engine bay that is just as strong as its aluminum predecessor, but weighs 60% less, improving fuel efficiency. You can create a custom fixture for a CMM inspection machine in 24 hours that would have taken 2 weeks and 5 times the cost to machine from a block of metal. You are combining the design freedom of 3D printing, the ability to create complex internal geometries and organic shapes, with a material strength that was previously only available through traditional manufacturing. It's about creating lighter, stronger, smarter parts, faster than ever before. We have officially pushed polymers to their absolute limit, infusing them with the heart of advanced materials to make them strong enough to stand toe-to-toe with aluminum. But what happens when that's still not enough? What happens when you need the thermal resistance to withstand the heat of a jet engine, the conductivity to create a custom heatsink, or the sheer unyielding strength and hardness of tool steel? What happens when you need a part that doesn't just replace metal but is metal? That's when we stop trying to imitate it, and we start printing it. This is a whole new dimension. We're not just simulating the properties of metal anymore. We're harnessing the atom itself. Welcome to the world of direct metal laser sintering, or DMLS. Imagine a sealed chamber and inside, a flat bed covered by a layer of metal powder so fine it's like dust. This isn't just any powder. It's a highly engineered, perfectly spherical alloy. Above this bed, a powerful laser, guided with microscopic precision by your digital design, zaps the powder. In that instant, the temperature skyrockets, melting and fusing those tiny metal particles together into a solid spot. Then a roller spreads another whisper-thin layer of powder on top, and the laser goes to work again, fusing the new layer to the one below it. Layer by agonizingly precise layer, your solid metal part grows, emerging from this sea of powder like a lost relic being unearthed. This isn't your desktop FDM printer extruding a line of plastic. This is controlled high-energy welding on a microscopic scale, over and over again thousands of times to build something from nothing. And the materials available are staggering. Let's start with the workhorse, the undisputed champion of versatility. Stainless steel 316L. If you're new to metal printing and need a default, this is often it. 316L is a fantastic all-rounder. It possesses excellent strength and ductility, meaning it can take a beating and bend before it breaks. But its real claim to fame is its superb corrosion resistance. This is the same grade of steel used in marine hardware, surgical instruments, and food processing equipment. Think about printing custom boat fittings that will live in salt water, or a specialized one-of-a-kind kitchen tool that needs to be sterilized, or even a unique, durable piece of jewelry. Because it's so well understood and relatively cost-effective for a printed metal, 316L is the gateway for many engineers and designers into the world of additively manufactured metal. But what if weight is your enemy? What if every single gram counts? Then you turn to aluminum, specifically an alloy like LC10Mg. This is the go-to material for lightweighting applications. It has a fantastic strength-to-weight ratio, making it a darling of the aerospace, automotive, and high-performance drone industries. Imagine you're building a custom race car. You could design a suspension bracket that is topologically optimized, a process where software carves away every last bit of non-essential material, leaving an almost alien skeletal structure that is stronger and dramatically lighter than its bulky machined counterpart. That's the power of printing in aluminum. It's not as hard or corrosion resistant as stainless steel, but when you need to fly higher, drive faster, or be more efficient, aluminum is your ticket. And then there's the superstar, the material that sounds like it's straight out of science fiction: titanium. Usually the alloy is T64, which is an alloy of titanium, aluminum, and vanadium. Titanium is the material for when there are no compromises. It's about 45% lighter than steel but can be just as strong. Its corrosion resistance is legendary, almost on par with platinum. And most critically, for some applications, it is biocompatible. Your body doesn't reject it. This combination of properties makes it the gold standard for high-stakes applications. We're talking about custom-printed hip implants and spinal fusion cages, perfectly matched to a patient's anatomy. We're talking about critical aerospace components like landing gear brackets for a jet, where failure is not an option, or high-end consumer goods, like a bespoke, ultralight bicycle frame printed as a single beautiful piece. Of course, this level of performance comes at a premium. Printing in titanium is expensive, but for applications where you need the absolute best, it is worth every penny. But the rabbit hole goes deeper. We've covered the big three, but online services are now offering superalloys that push the boundaries of physics. Take Inconel 718. This isn't a metal, it's a statement. Inconel is a nickel-chromium superalloy designed to not just survive, but thrive in the most extreme environments imaginable. We're talking about places with blistering heat and crushing pressure. Think turbine blades inside a jet engine, where temperatures can exceed the melting point of many metals, or exhaust manifolds for a Formula One car, glowing red-hot while withstanding intense vibration. Printing in Inconel allows engineers to create components with internal cooling channels and complex geometries that are impossible to machine, unlocking new levels of performance and efficiency in these hellish environments. Let's go back to that heatsink example. What if you need the absolute best thermal conductivity? You need copper. Pure copper printing is a more recent development, but it's a revolutionary one. Copper is notoriously difficult to work with in laser-based systems because it's so reflective, but services have cracked the code. Now you can print a heatsink with an internal lattice structure so complex it looks like a coral reef, maximizing surface area in a tiny volume to dissipate heat with unparalleled efficiency. This is a game changer for high-performance computing, custom liquid cooling blocks for processors, and even components for rocket engine combustion chambers. And what about the other end of the spectrum? Not heat, but pure brute force and wear resistance. For that, we have tool steel like H13. This is the material you use to make the tools that make other things. It's incredibly hard, tough, and resistant to thermal fatigue. Traditionally, if you needed a custom mold for injection molding, or a specific die for stamping metal, you'd be waiting weeks or months for a toolmaker to machine it from a solid block. With 3D printing, you can print a complex mold insert with conformal cooling channels that perfectly follow the contour of the part, overnight. This drastically reduces cycle times in manufacturing and allows for rapid iteration of a product's design. It's a fundamental shift in how quickly we can go from idea to mass production. So why go through all this trouble? Why use a high-energy laser to painstakingly build a part from dust when we've been casting and machining metal for centuries? The answer is complexity. Metal 3D printing's true power isn't making existing parts cheaper. It's about making entirely new parts possible. It's about part consolidation, taking an assembly of 20 different brackets, plates, and fasteners and printing it as one single, stronger, lighter component. It's about the freedom to design parts that mimic the elegant, efficient structures found in nature, like bone, which are only as dense as they need to be exactly where they need to be. But it's crucial to be realistic. This technology is not a magic bullet. First, the cost is significant. The raw powder is expensive, the machines cost millions of dollars, and the process is energy intensive. This is for high-value applications where the performance gains justify the price. Second, the parts don't come out of the printer ready for prime time. They have a slightly rough, matte surface finish from the sintered powder. They are attached to a build plate by support structures that need to be carefully removed. And often they require post-processing, like CNC machining on critical surfaces to achieve tight tolerances, or heat treatment to relieve internal stresses and optimize the material's properties. All of this adds to the final cost and lead time. And finally, you have to design for the process. You can't just take a CAD model designed for machining and send it to a metal printer. You have to think about thermal stresses that can warp the part as it cools, the orientation on the build plate, and where to place support structures. It's a new way of thinking, a skill set called Design for Additive Manufacturing, or DFAM. The leap from printing with plastics to printing with metals is as significant as the leap from the typewriter to the word processor. It fundamentally changes the rules of what can be designed and manufactured. It allows for a level of customization and performance optimization that was, until very recently, the stuff of dreams. We can now create parts that are impossibly complex, unbelievably light, and brutally strong. But our material journey isn't over. We've explored the world of rigid plastics and unyielding metals. But what happens when you need the opposite? What if you need a part that can stretch, bend, compress, and snap back into shape? What if you need to print not a solid bracket, but a flexible seal, a soft touch grip, or a shock-absorbing bumper? For that, you enter the world of elastomers. This isn't just a single material, but a whole family of polymers defined by their incredible elasticity. They are the shapeshifters of the 3D printing world. Think of the difference between a brick and a sneaker sole. One is designed for compressive strength and rigidity. The other is engineered to absorb impact, flex with every step, and return to its original shape millions of times. That's the magic of elastomers, the undisputed champion in this category, and the material you'll see offered by nearly every major US service is TPU, or thermoplastic polyurethane. TPU is a remarkable hybrid. It bridges the gap between rigid plastics and soft, pliable rubbers. It's tough, it's durable, it's resistant to abrasion, oils, and greases, and its primary superpower is, of course, its flexibility. But flexibility isn't a simple on or off switch. It's a spectrum. And to navigate that spectrum, you need to understand one of the most critical properties for these materials: shore hardness. When you look at a datasheet for TPU, you won't just see TPU. You'll see something like TPU92A or TPU85A. That number and letter combination is its shore hardness rating, and it tells you exactly how soft or hard the material is. Think of it like this: the Shore scale is for softer, more rubbery materials. A gummy bear might be around 20A. A typical rubber band is about 25A. The sole of your running shoe could be around 60A. A car tire is harder, maybe 70A. As you approach 100A, the material gets much stiffer. That TPU92A you see on printing services? That's a very common, firm but flexible material. It's like the hard rubber on a shopping cart wheel. You can deform it, but it takes some force. An 85A would be noticeably softer and easier to bend. Then there's the Shore D scale, which picks up where the A scale leaves off, measuring harder plastics. A golf ball is about 50D, and a construction hard hat is around 80D. Understanding this single metric is the key to getting the exact flexibility you need. So, how do services print this stuff? For production-grade TPU parts, the top technologies are selective laser sintering, or SLS, and multi-jet fusion, or MJF. Just like with nylon, these processes use a bed of fine powder. A laser or a fusing agent solidifies the TPU powder layer by layer. The result is a part with incredible toughness and tear resistance. Because it's a powder bed process, you can create incredibly complex, flexible geometries, like intricate lattice structures for cushioning, without any need for support material. These parts have a slightly grainy surface finish, but their mechanical properties are outstanding, making them perfect for final products like seals, protective bumpers, flexible couplings, and even custom shoe midsoles. On the other end of the spectrum is fused deposition modeling, or FDM. You can get TPU as a filament, and it prints much like PLA or ABS, but it requires a specialized extruder that can handle the flexible spaghetti-like strand without it buckling. FDM-printed TPU parts are fantastic for rapid prototyping. You can quickly test the fit and feel of a flexible grip, a watch band, or a phone case. What's more, with FDM, you can manipulate the part's flexibility not just by choosing a different shore hardness, but by changing the print settings. A part printed with 100% infill will be much stiffer than the same part printed with a 20% honeycomb infill and fewer outer walls. This gives designers an extra layer of control over the final feel of their prototype. But TPU isn't the only player in the game. What if you need something with even higher temperature resistance, or something that is certified to be skin safe or even food grade? This is where you might encounter silicone, or more accurately, silicone-like materials. True silicone is a thermoset, not a thermoplastic. That means once it's cured, it can't be remelted, which makes it very difficult to 3D print directly using common methods. However, advanced technologies like polyjet and carbon DLS have made incredible strides here. Polyjet technology, for example, works like an inkjet printer, but instead of depositing ink, it jets tiny droplets of a liquid photopolymer that are instantly cured by UV light. By mixing different photopolymers, these machines can create materials that mimic the properties of silicone with stunning accuracy, right down to the specific shore hardness value. These silicone-like materials are perfect for applications where TPU falls short. They often have a much higher operating temperature range, making them suitable for gaskets in heated environments. Certain grades are biocompatible and can be sterilized, making them invaluable for creating realistic anatomical models for surgical planning or custom medical device prototypes that will be in contact with skin. Their smooth, non-porous surface finish is also a major advantage over the grainier texture of powder-based TPU. The trade-off is typically cost. These advanced materials and processes are more expensive, so they are reserved for applications where their unique properties are an absolute necessity. So as we stand back and look at the entire landscape we've explored over this series, a clear picture emerges. We started with the basics, the everyday workhorses like PLA and ABS, perfect for visual models and simple prototypes. We moved up to the engineering-grade thermoplastics, the tough-as-nails nylon, the dimensionally stable polycarbonate, and the versatile PETG materials that allow us to print functional, end-use parts that can withstand real-world stress. We then ventured into the specialized world of high-performance polymers like PEEK and Ultim, materials that push the boundaries of what's possible, operating in extreme temperatures and harsh chemical environments where others would fail. We saw how resin-based printing with SLA and DLP unlocks a universe of impossibly fine detail, creating parts that look more like injection-molded products, perfect for everything from jewelry to dental aligners. We demystified the process of printing in solid metal, exploring how DMLS and binder jetting are revolutionizing aerospace, medical, and automotive industries by creating complex, lightweight, and incredibly strong metal components that were previously impossible to manufacture. And today, we've completed the circle by delving into the flexible, elastic world of TPUs and silicones, giving us the ability to print the soft parts that complement the rigid. The journey from a simple plastic filament to a laser-sintered titanium alloy or a flexible, rubber-like seal is a testament to how far this technology has come. The key takeaway from all of this is that the material is not an afterthought. It is a foundational design decision. The choice you make from that drop-down menu on a service's website will dictate the strength, the weight, the cost, the heat resistance, the chemical resistance, and the feel of your final part. You now have the framework to make that decision with confidence. You can look at a technical data sheet and understand what tensile strength, heat deflection temperature, and shore hardness actually mean for your project. You know that if you need a snap-fit enclosure, nylon 12 is a fantastic choice. You know that if you need a transparent lens prototype, polycarbonate or a clear resin is the way to go. You know that if you need a lightweight bracket that's stronger than steel, you can turn to aluminum or titanium. And you know if you need a shock-absorbing gasket, TPU is your answer. The power of modern manufacturing is no longer locked away in massive factories. It's accessible through your web browser. With the knowledge you now have, you can leverage that power more effectively than ever before. You're no longer just uploading a file and hoping for the best. You are making informed, intelligent engineering choices. You are designing for the material, for the process, and for the application. So take this knowledge, build something incredible, and be a part of shaping the future of how things are made.